So in the previous session, we have discussed about periodic motion. Then we are talking about spring mass system, simple pendulum, and we have seen at some equations like some sinusoidal combination of sine plus cos, some little bit complex equation which we have simplified and proved okay, which are simple harmonic motion, and we have studied about some exponential function and logarithmic function, and we have proved that they are not periodic motions. Okay. Then now further continuing. Okay. Let us understand what actually this simple harmonic motion is. So we will be doing further. We'll go deep into simple harmonic motion, which is a part of oscillation. So SHM, simple harmonic motion. So yeah. So this is what you see in the picture is like a particle vibrating back and forth about origin in x-axis between limits plus a to minus a. Okay. So this so this is a particle. This is the particle, and let us say this is the origin. Okay. So this particle vibrates back and forth, back and forth about origin in x-axis between limits plus a to minus a. So this particle is moving from plus a to minus a. Okay. Um, so you might have done in your experiment some tuning fork. Okay. So your tuning fork is something like this tuning fork. Okay. So there you hit the tuning fork and see how it's this legs of the tuning forks are vibrating. Okay. So this leg you hit it on the table or and you see how this fork leg is vibrating. So you can observe that this leg is vibrating something like this, right? This leg is vibrating something like this. So this is a kind of vibration where the particle moves from plus a to minus a above the origin O. Okay. So the this motion we have simplified it in this picture. Okay. So this red dot is your the particle, like where the particle lies. Okay. And let us say the time period is t, and we have told that time period is something after which the motion repeats itself. Okay. So here at time t is equal to 0, let us say the particle is at the extreme position. Okay. So at a particle at the extreme position, it will try to go back to its original position. So at time t is equal to 4, it has reached the center. Okay. So after it reaches the center, it has a tendency to overshoot that equilibrium, that origin. So it has overshooted, and it has at time t is equal to 2 times small t is equal to t by 2. That is the half of the time period. From this point, it has moved to this point. And at time t is equal to capital 3t by 4, 3t by 4, it has again gone back to origin. Okay. And once again it has gone back to origin, it has again a tendency to overshoot and go back to this. So you can see at time t is equal to 0, this red particle here is here, and at time t is equal to t, the red particle is again here. So the motion will get repeated. Okay. Now why I am telling the velocity is maximum here? Because when it reaches the center, the velocity is maximum. That will study actually. So in case of a pendulum, let us say in case of a pendulum, okay. So you imagine this one, if this particle, you imagine this has gone up to this has, so it will have two extreme position. So it will have two extreme positions. So this this corresponds to this point, first point. Okay, it is the first point. You just pull the pendulum and you release the pendulum, and if you imagine that there is no air resistance, the pendulum will go like this. The pendulum will go like this, then it will go like this. It will overshoot by equilibrium position, then it will come back like this, then it will go like this. Okay. It will go like this. So this is in case of a simple pendulum. So starting from this position and again coming back to this position, that is the time period. Okay. Then uh, the velocity of this pendulum at this extreme position will be zero, whereas at the center the velocity will be maximum. So that's what is being told here. At the origin, the velocity is maximum. Okay, and then after t, let us say when small t is equal to 5t/4, then again it will okay. I think it will at 5t/4. It will not be here. It will be here. Okay. Right. Right. Right.
Okay.
It will be here. Okay. So again, like that means this is t/4. You add capital T to this. This is nothing but capital T plus t/4, which is nothing but 5t/4. So this repeats this.
Yes.
There is a repetition. So if you add t/4 plus t, this is 5t/4. Similarly, if you add t/2 plus t, this will get repeated. Okay, so that is the meaning of like this simple harmonic motion. So a generalized equation for this simple harmonic motion is x is equal to a cos omega t plus phi. So this is either a sinusoidal function or a cosine function, similar only where it starts that will differ. Otherwise, the shape and amplitude, everything will remain same. Okay, so in this equation, every term has got its significance. Okay, so this is your x, this is your amplitude, this is called your angular velocity or angular frequency. Okay, this is time. Time is the variable. It is the independent variable. X is the dependent variable. Okay, so x is displacement. Okay, phi is called phase constant. Okay, I'll explain what it exactly is phase constant. And in your y-axis, this is displacement. Okay. In your y-axis, the displacement. In your x-axis, it is time. Okay. So these two curves, the red one and the green one, are actually this curve, this green one and red one. So let us say this is the both are representing a cos omega t plus phi. Okay. Both are representing a cos omega t plus phi. Okay. So when phi is equal to 0, okay, when phi is equal to 0 and time t is equal to 0. If the phase constant is 0, anyway you know time t, here it is origin, so that's why the time is equal to 0. If at origin, when time is equal to 0, if the phase constant is also 0, that is a angle. Phi is nothing but an angle. Omega t is also nothing but an angle. So when the phase constant phi is equal to 0 and at time t is equal to 0, which is at the origin, you will get this green curve. Okay. So why? Because if time t is equal to 0, it will become a cos 0. A cos 0 degree. So a cos 0 is nothing but your a, capital A. So the amplitude will be maximum here. So this green curve represents a curve with phase angle is equal to 0. And green curve. This red curve, it represents phi is equal to phi. This is the green curve. This green curve, sorry, this green curve represent phi is equal to 0, whereas this red curve represent phi is equal to pi by 4. That phase constant is equal to pi by 4. Okay, so you can see the at time t is equal to 0, what will be that equation? A cos omega t is anyway 0, so it becomes a cos pi by 4, right? So a cos pi by 4 is nothing but pi by 4 is some root 2, right? Yeah. Root 2. So here this is root 2, like area divided by root 2 is 1.1 a by 1.414. So this is nothing but a by 1.4414, right? A by root 2 or nothing but a by root 2. So uh, the amplitude for both red and green curves, the amplitude remains the same. Okay. Only difference is the phase constant, right? The angular frequency or the angular velocity omega is same. Only difference is the phase constant. So it starts at a phase is equal to pi by 4. At 45 degree it starts. Okay. So now we'll uh, we'll find out what is the angular velocity or angular frequency. Okay. So here you know uh, time time capital T is taken to traverse angle 2 pi, right? So in time t it is covering 2 pi angle, right? So if time, so corresponding to linear motion, in angular motion we define things in terms of theta, right? So in linear motion we are saying t uh, time taken in time it has covered distance x. In angular motion, we are saying in time t it is covering angle theta. So here it has taken capital T time to cover angle 2 pi. Like what do you mean by 2 pi angle? Like it is covering just one circle. Okay, so like this is 0, this is pi by 2, this is pi, this is pi, and this is 3 pi by 2, and again it is 2 pi, right? So in one circle, it is covering 2 pi angle. So in time t, it has covered 2 pi angle. So you know that distance per unit time is equal to velocity. In linear velocity, distance per unit time is equal to linear velocity, right? X by t. Similarly, angular velocity, it is angle covered per unit time. So angle in this case, it has covered 2 pi angle in time period t. Okay. So angular velocity or angular frequency is equal to 2 pi by 2. Okay. So that is the takeaway, like angular frequency or angular velocity is equal to 2 pi by t. Okay. So now let us solve one example. Okay, can you take a picture of this? Let us solve one example where the equation is a combined equation which is not a simple sinusoidal or cosine function, which is little bit complex, we'll simplify it into a sinusoidal or cosine function, and then we will say what is the amplitude, what is the angular velocity, and what is the time period. If we compare with the simplified equation, we can arrive at it. Okay. Okay. So we'll solve one example where, like, let us say, which of the following function of time represent a simple harmonic motion, periodic but not simple harmonic? Give the period for each case. Okay. So we have equation sin omega t minus cos omega t. The question is whether it is simple harmonic or not. So we have told that simple harmonic is like we have told it is x is equal to a cos omega t plus phi. This is simple harmonic. Or it can be a sin omega t plus phi, whatever. Like that does not matter whether cosine or sine. We know this is amplitude, this is angular frequency, and phi is phase constant, right? So this my question is sin omega t minus cos omega t. Okay. So this becomes like sin omega t minus, cos omega t, like that trigonometric formula, right?
Sin
You
omega
know
t.
the yeah, sin 90 minus theta is equal to cos theta. Similarly, cos 90 minus theta is equal to sin theta.
Yes.
This you should always remember. 90 minus in first quadrant everything is
Positive.
positive. Whereas sin 90 plus theta is equal to cos theta. That is correct. Sin 90 plus theta is equal to cos theta. Whereas cos 90 plus theta is equal to minus sin minus sin theta. These things you should always remember. So anyway, so just remember, like cos or sin 90 minus theta, if the angle is in the first quadrant, it will be always positive. So sin omega t minus sin 90 minus omega t, right? So this is my equation. Okay. Hmm. Sin 90 minus omega t. Okay. So this equation can be written as, like, say, this equation can be written as 2 cos pi by 4 into sin omega t minus pi by 4. Okay. So cos pi by 4 is nothing but 1 by root 2. So 2 into 1 by root 2 into sin omega t minus pi by 4. So this becomes root 2 sin omega t minus pi by 4. So now you will have the question how we came from here to here. Okay. So this formula is nothing but you might have studied in your trigonometry sin A minus sin B formula. Okay. So sin A minus sin B. You have already written here what you have written. Just read out what you have written. Sin A minus sin B. What is the formula?
2 cos A plus B by 2 into sin A minus B by 2.
So A plus B by 2 and A minus B by 2. So from this, if you remember this formula, then you can do it. Okay. So in the previous class, we were discussing about sin A plus B formula. That is, everyone should remember, or cos A plus B. Similarly, sin A minus sin B, that formula also need to be remembered. You should remember that, okay, this is the formula. Okay. So once you know this will get simplified. Okay. So now the question is, like simple harmonic motion. Okay. So that means this represents a simple harmonic motion. Why? Because if we compare it with A sin omega t plus pi. If this is simple harmonic, this is also simple harmonic. That's why you simplify your little more complex equation into this form, in the form of a cos or a sin. Then if you are able to simplify it, it is a simple harmonic motion. So you have simplified it into this. That means your A is root 2, that is your amplitude. Okay. And then your phi is equal to minus pi by 4. This is your phase constant. Okay. So similarly, another question is like your sine square omega t. Okay. Whether sine square omega t is simple harmonic or not. Okay. So that also you have to remember your trigonometry. This sine square omega t. Okay. Sine square omega t. Okay. So this is equal to half minus half cos 2 omega t. Half cos 2 omega t. 2 omega t. Okay. Cos 2 omega t, not omega t, 2 omega t. Okay. So this sine square omega t can be simplified as half minus half cos 2 omega t. So this square term you are simplifying it into a not the sine you are converting into cos term. Also this square you are trying to avoid because you want to compare with a linear term, not with a square term. That's why the square term you are simplifying it into a linear term, not a square of the cos term. If it is square of the cos, you cannot compare. So this is your equation. This you can compare with, let us say x is equal to a cos omega t. Right? So this just forget this half is a constant. So you compare here like here earlier we were saying time period is equal to 2 pi by omega. In this case, in this equation, the time period will become equal to pi by omega. Right? The time period will be decreasing. Okay, the frequency will be more, time period will be less for this particular way. Because if you multiply this pi by omega into this is 2 pi by omega, then the pi by omega into uh, yeah, so omega will become pi by t, right? Pi by t. Then pi by t into 2. It will become 2 pi by t. See, omega will be, if t is equal to pi by omega, omega will become pi by t. So this pi by t into 2. That will, this term will become 2 pi by t. Yeah. Which is what your angular frequency is. So it is a wave with different angular frequency. That's all. It's a wave with different time period. One has 2 pi by omega, one is pi by omega. So time period has decreased here, frequency has increased. Okay. That is the only difference. Okay. So these are some of the equations you, so always if it is a complex equation like this, your aim is so to simplify it, you should always by heart the trigonometric formula without by hearting the trigonometric formula. So that's why it is always important to memorize the trigonometric formula. There is no other way. You cannot derive everything in the exam. You have to remember certain things. Okay. Without remembering, you cannot do, especially for MCQ questions. You have to remember formulas. There is no other option. Okay, so this formula you have to remember. And to compare something with something, a equation like this, you have to simplify this complex equation into a simplified equation. This is one complex equation, you have simplified into this. Similarly, this is one complex equation, you have simplified into this. Clear? Yes. Take a picture of it. Okay, so we have now covered the generalized form of simple harmonic motion, the equation x is equal to a cos omega t plus pi, omega is your angular velocity or angular frequency, a is your amplitude, pi is your phase constant, and whether it is a sinusoidal wave or it is a cosine wave, it does not matter because if you put here pi by 2, this sine will become cos. Okay, so sine or cos it does not matter, but in general we are comparing with cos. Sine doesn't matter actually. So and we have simplified some combined equation into a simplified equation in terms of sine or cos. And here we have a square term that also we have simplified it into a linear term. We have simplified it into a linear term so that we can compare. And we have shown that okay, sometimes for this particular equation, the time period is different. So it is a sinusoidal wave or it is a simple harmonic motion. So it is a simple harmonic motion and it has different frequency. So it is a simple harmonic motion. Its frequency can be it is a simple harmonic motion. Its angular frequency, its time period or frequency can be different. So here the time period is pi by omega, which is half of that of the original one, and this is that means time period is less means frequency is inverse of time period. Okay, so this in the next session we will cover simple harmonic motion in relation to a circular motion. If a particle is moving in circle, the projection of the particle on the axis, either the x-axis or y-axis, like when in a circular motion a particle is moving, in the horizontal line, let us say you are drawing two horizontal lines, perpendicular, one horizontal and one vertical line perpendicular to each other. A particle is moving in the circle. The projection of that particle on the x-axis is cos omega t. Projection of the particle on the y-axis is sin omega t. So with reference to that, we'll do that circular motion and then compare it to the simple harmonic equation, and then we'll derive the expression for velocity and acceleration in simple harmonic motion. Then after completing that, we'll derive the time period for a spring mass system, then time period for a simple pendulum. So once we cover spring mass system and simple pendulum, so we'll be almost at 12th level. We'll be completing the simple harmonic motion without spring mass system and simple pendulum derivation. The simple harmonic motion is incomplete. So that will be the completion of simple harmonic motion. Then you have something related to damped simple harmonic motion or the oscillation. What is damping and what is post vibration, that also will cover a bit. Okay. So in the next session, we'll do the circular motion, a particle moving in a circle, and then how it is in relation to the simple harmonic motion, and then we'll derive the velocity and acceleration in simple harmonic motion. Then next to that, we'll do the spring mass system and then the simple pendulum. Okay. Beyond that, we will do damped simple. So all that what we are doing till now, it is on damp. We are telling air resistance is zero, friction is zero. Then only it will be simple harmonic. If there is friction, if there is resistance in the air, then it will not vibrate indefinitely. Okay, so these are all ideal cases, but actual case is that presence of friction, presence of air resistance, that is otherwise called damping. So we will talk about damping after completing the ideal simple harmonic motion, spring mass and the pendulum. Okay, okay. Thank you.